really the only formula we need out of here is Snell's law. I'm going to go through some interesting stuff from the chapter. I'm just going to use the PowerPoint here. We won't even write anything down. But really the only formulas you're going to need are Snell's law and our critical angle. Okay, so we're talking about reflection and refraction here. If we have some kind of mirrored surface, a flat mirror, and an incident ray of light coming in, it will reflect off that flat surface at the same angle in which it's incident. The angle of incidence equals the angle of refraction. And everything we're talking about today, we're always talking about the angle from the normal. So if I say I have a 30-degree incident ray, that means right here is a 30-degree, not the angle between the ray and the surface. The angle between the ray and the normal to the surface. So if we're coming in at a 30-degree angle, we'll reflect back out at a 30-degree angle. Okay. We also have this phenomenon called refraction. So say we have two different materials here, air and water. Light's coming in. Some of that light will reflect off. The surface of the water will act like a mirror. You know that. You've seen reflections in a mirror before, or in the surface of the water. But some of that light will go straight into the water, but at that boundary, the light gets bent. It's because the speed of light in different materials is different. The c, 3 × 10⁸ meters per second that we use for the speed of light is the speed of light in a vacuum. In different materials, light moves at different speeds. So because of that, there's a nice diagram that kind of explains that in a minute. Because of that, light gets bent when it moves from one medium to another. And we call that refraction. So this light ray is coming in, some of it reflects, some of it goes straight through, but instead of coming straight, it gets bent either toward the normal or away from the normal. Okay, and that has to do with what we call the index of refraction, which is the speed of light in a vacuum divided by the speed of light in that material. So for anything other than a vacuum, the index of refraction is going to be bigger than 1. So here are some indices of refraction. You don't have to memorize these, of course, but air is almost 1. In fact, in any problem you see, if you have a homework, well, I didn't even build homework for this because you'll have like one question on the final about it. But if you see lights going from air into glass or air into water, air is so close to 1 that we just say 1 for air. But look at water. The speed of light in water is at something like 33% slower than the speed of light in air. And I'm just approximating there, but light moves much slower in water, so we have a higher index of refraction. Okay, and here's a good analogy that we like to use. Imagine that we have this plane wave of light coming at water. Imagine you and a bunch of your buddies stand in a line holding hands. So this line here represents you and all your buddies standing in a line, you're holding hands, and you're walking at this angle here toward the water. Well, once the first person here hits the water, they're going to get slowed down. I mean, just imagine walking into water. You can't walk as fast in water as you can on land. So you're going to get slowed down, and what you're going to end up doing is dragging the guy next to you. So as you're walking here, that line that did look like this is going to get tilted, and as you guys get into the water, now your line is going to be walking down like this. So now look at the line of guys holding hands. And it's because this first guy, when he hit the water, got slowed down. Then the next guy got slowed down, and so forth. So that plane wave that was coming in at this angle is now going through the water at this angle. And the relationship between all this is called Snell's law. This is the one formula you want to write down. N1 sine theta 1 equals N2 sine theta 2. You may have seen this back in 8th or 9th grade science class. You may have actually done this before. So this is side 1, this is side 2. We have the index of refraction and the angle from the normal, and then similarly on the other side. We're usually looking for theta 2. So we're usually given both indices of refraction, given our angle of incidence, and we're looking for this, our angle of refraction. Now this works either way. A light ray coming this way from water would get bent away from the normal going into air. And a light ray coming in air, let me think about this for a minute. Oh, I may have had these backwards. Now that I'm looking at the picture, I may have had these backwards. This would be the water and this would be the air. Yeah. If you're going from a lower to a higher index of refraction, your light ray gets bent away from the normal. If you're going from higher to lower, you get bent toward the normal. So going this direction would be going from water to air, and this would be air to water. Okay, so we could look at this picture here and figure out who has the higher index of refraction. Now you can memorize this stuff I'm about to say, but it's really like you could easily just do the math and figure it out. It's not that big a deal. You don't have to memorize what I'm about to say, but it is interesting. This light ray here wants to come straight through, but instead of coming straight through, it got bent. It got bent away from where it normally would have been. You get bent away from the normal when you're going from higher to lower. So N2 is less than N1. Going through this interface, we got bent toward the normal. The light ray would have come straight through, but it got bent toward this normal. So that means N3 must be less than N1. Wait, let me make sure I said that right.
I think you mean more than.
More than, yes. N3 is bigger than N1 because we got bent toward the normal. Again, I figured that out on the fly. You don't have to memorize those facts. They are kind of interesting. Where that comes into play, where we care about that, is total internal reflection. This is what's interesting. That's when this matters. So here I've got light in water coming up, hitting the surface of the water and coming out into air. So that light ray got bent away from the normal. Well, if the indices of refraction match up right, this away from the normal could be bent far enough that this angle could even be bigger than 90 degrees. And we call that the critical angle. So imagine if this light ray comes up and it gets bent so far that instead of going up here into the air, it just rides along the top of the water. Well, that would mean our angle of refraction is 90 degrees. So if we go back to Snell's law, if we set this theta equal to 90 degrees, sine of 90 is 1, we get sine of theta 1 equals N2 over N1. We call that total internal reflection. So instead of passing through, all the light gets reflected. Remember, some of the light always gets reflected. In this case, if our angle is bigger than that critical angle right there, all the light gets reflected. This is how fiber optic cables work. This is why we have internet. A lot of the internet travels through fiber optic cables. That's just light bouncing around in glass tubes and plastic tubes. And the index of refraction is set up so that these have a really high critical angle, so that the light bouncing around will always get reflected and not pass through the surface. So this fiber optic cable can bend around all over the place and all the light will just tunnel right through it. Okay, now everything we've said is actually only for monochromatic light, light of one color. If you have light of different frequencies, different wavelengths, different colors, each frequency has its own different index of refraction. So if I have white light coming in, what actually happens is the light gets bent at a different angle for each different color. Purple gets bent more than red does. That's how a prism works. So white light comes in, that light gets spread out, and then if we allow it to go through another side, it will get spread even more, and that's how a prism turns white light into the colors of the rainbow. This is how rainbows are formed. So we've got air droplets in the air, light from the sun will come in, and as long as our angle between the observer and those rain droplets is less than 42 degrees, that's our critical angle here, then that light gets dispersed into all the different colors of the rainbow, and our observer down here can see a rainbow. A rainbow is actually a perfect circle, but we can only see the top half of it because the bottom doesn't really exist. So anytime you're seeing a rainbow, that's always because the sun is at your back. That's the only time you can see a rainbow. The sun's behind you and it's being dispersed on the rain droplets in front of you. And that angle has to be less than 42 degrees.